The universe is not stable. In 2012, physicists measured the Higgs boson at 125 giga-electron volts and realized we are living in a false vacuum. That measurement confirmed our reality sits in a temporary energy state, not the lowest possible one. The Higgs field, the invisible force that gives every particle its mass, could tunnel to a lower state at any moment. When it does, a bubble of true vacuum will nucleate somewhere in space and expand at light speed, erasing everything. No warning, no escape. The laws of physics inside that bubble will rewrite themselves. Atoms will disintegrate. Matter will cease to exist as we know it. This is not speculation. This is what the math predicts. The Standard Model, our most successful theory, says the universe can and eventually will delete itself. The only question is when. If you want to understand the particle that holds reality together and could rip it apart, hit that like button and subscribe. Prepare yourselves. We begin. July 4th, 2012. CERN's Large Hadron Collider detected something that should not exist according to older theories. Scientists observed a new particle with a mass of 125 giga-electron volts appearing in the debris of proton collisions. The signal was unmistakable. After smashing particles together trillions of times and sifting through mountains of data, two independent detector teams, ATLAS and CMS, saw the same thing. A particle that lived for only a fraction of a second before decaying into lighter particles, but its signature was clear. This was the Higgs boson. Peter Higgs had predicted this particle almost 50 years earlier in 1964. He proposed that an invisible field permeates all of space. Particles moving through this field experience resistance, and that resistance is what we call mass. Without the Higgs field, electrons would be massless. They would fly through space at light speed, unable to bind to atomic nuclei. Atoms could not form, chemistry would not exist. Stars, planets, and life would be impossible. The field is not optional. It is the reason matter has substance. But the field needed proof. Theories mean nothing without experimental confirmation. For decades, physicists built larger and more powerful colliders, trying to create the Higgs boson in the lab. The particle is a ripple in the Higgs field itself, a quantum excitation that appears when enough energy concentrates in one spot. Creating it required smashing protons together at 99.99% the speed of light. The Large Hadron Collider, a ring 17 miles in circumference buried beneath Switzerland and France, was built specifically for this purpose. When the announcement came in 2012, champagne corks popped in laboratories worldwide. The Nobel Prize followed in 2013. Headlines celebrated the discovery as the final piece of the Standard Model of particle physics. Every fundamental particle predicted by theory had now been found. Physics was complete. But physicists were not celebrating as loudly as the public thought they should be, because the Higgs mass measurement brought a disturbing realization. 125 giga-electron volts. That specific number matters more than anyone outside the field understood. It sits in a narrow range that cosmologists call the metastable region. If the Higgs mass had been slightly heavier, say 140 giga-electron volts, the universe would be completely stable. The vacuum would be the true lowest energy state, and we could sleep soundly knowing reality is permanent. If it had been lighter, below 115 giga-electron volts, the vacuum would be catastrophically unstable. The universe would have already destroyed itself long ago during the Big Bang. Instead, we got 125, right in the middle. The measurements combined with the known mass of the top quark, which also affects vacuum stability through quantum interactions, placed us in a zone physicists did not want to be. The vacuum is stable enough to have lasted 13.8 billion years, but it is not the ground state. It is a false vacuum, a temporary configuration. Think of a ball resting in a shallow bowl on a hillside. The ball is stable in the bowl. It will not roll out easily, but there is a deeper valley farther down the hill. If the ball could somehow get over the rim of the bowl, it would roll downhill to the true lowest point. The Higgs field is that ball. Quantum mechanics provides a way over the rim. It is called tunneling. In the quantum world, particles do not need to climb over energy barriers. They can borrow energy from uncertainty itself and appear on the other side. The probability is incredibly small, but it is not zero. The Higgs field, sitting in its false vacuum, has a non-zero probability of tunneling to the true vacuum at any moment. When that happens, the consequences are absolute. Therefore, the 2012 discovery was not just a confirmation of theory. It was a warning. The particle that gives us mass that makes our existence possible is also the mechanism of our destruction. The universe has an expiration date written into its fundamental structure, and we just read the label. Space is not empty. This contradicts intuition, but it is true. Even in the darkest void between galaxies, far from any matter or radiation, space itself contains energy. The Higgs field is one of these energies. It exists everywhere, at every point in the universe, with a specific value. That value is approximately 246 giga-electron volts. This is called the vacuum expectation value, and it determines how particles acquire mass. Picture the field as an invisible ocean filling all of space. Particles are objects moving through this ocean. Some particles interact strongly with the field, experiencing heavy resistance. These become massive particles like the top quark or the W and Z bosons. Other particles barely interact at all. Photons, the particles of light, pass through the Higgs field without resistance. They remain massless and travel at light speed. Electrons interact moderately, gaining a small mass. Quarks interact more strongly, gaining larger masses. The strength of interaction determines the mass. This is not a metaphor. The Higgs field is as real as the electromagnetic field or the gravitational field. It has measurable effects. When CERN measured the Higgs boson in 2012, they were detecting a ripple in this field, proof that the field exists and has the properties theory predicted. But the field's existence raises a question that cosmologists cannot ignore. Why does the field have the value it has? Why 246 giga-electron volts and not some other number? The answer involves potential energy. Every field in physics has a potential energy curve that describes how much energy the field contains at different values. For most fields, this curve is simple. It has one minimum, like a valley. The field naturally settles into that minimum because that is the lowest energy state. Systems in nature always move toward lower energy if possible. Water flows downhill, hot objects cool down, fields relax to their minimum energy configuration. The Higgs field's potential energy curve is more complicated. Calculations based on the standard model show that the curve does not have one simple minimum. At low field values near zero, the energy is high. As the field value increases, the energy drops, forming a valley around where we currently sit. But the calculations show something else. At much higher field values, billions of times larger, the energy drops again. There is a second valley, deeper than the first. The true minimum. We are not in the true minimum. We are in a local minimum, a false vacuum. The field is stable here in the sense that small disturbances will not kick it out. If you nudge the field slightly, it will oscillate and settle back. But there is a lower energy state available. The barrier between our current valley and the deeper valley is enormous, requiring the field to climb to incredibly high values before it can drop down the other side. Classical physics says this barrier is insurmountable. The field does not have enough energy to climb over, but quantum mechanics does not care about classical barriers. Quantum tunneling allows the field to jump from one side of the barrier to the other without climbing over. The probability depends on the height and width of the barrier. For the Higgs field, the barrier is high and wide, making tunneling extremely unlikely. But unlikely is not impossible. Given enough time and enough space, even improbable events eventually happen. When tunneling occurs, it does not happen everywhere at once, it starts at a single point. Quantum fluctuations cause a tiny region of space, perhaps smaller than an atomic nucleus, to spontaneously flip to the true vacuum state. In that region, the Higgs field suddenly has a different value. Particles interacting with the field acquire different masses. The fundamental constants of nature change. Physics is rewritten. This tiny bubble is not stable at a small size. The true vacuum has lower energy than the false vacuum. Energy wants to minimize. Therefore, the bubble grows. The boundary between the true vacuum inside and the false vacuum outside expands outward in all directions. And because the energy difference between the two vacua is enormous, the expansion is relativistic. The bubble wall moves at the speed of light. Nothing can outrun light. No signal, no particle, no force can travel faster. This means the bubble is undetectable until it hits you. You cannot see it coming. There is no warning. One moment you exist in the false vacuum where physics works as it always has. The next moment the bubble wall passes through your location and the Higgs field transitions to the true vacuum. The masses of particles change instantly. Electrons become heavier or lighter. Quarks change mass. The binding energy of atomic nuclei shifts. Atoms that were stable become unstable, chemistry breaks, molecular bonds snap. Your body, made of atoms held together by electromagnetic forces calibrated to specific particle masses, disintegrates. But this is not the worst part. The worst part is that the bubble, once nucleated, cannot be stopped. There is no mechanism in physics to reverse vacuum decay. The true vacuum is the ground state. The system has no reason to jump back to the false vacuum. The bubble will expand forever, consuming the entire universe at light speed, converting all of space to the true vacuum state. Everything that exists in the false vacuum, every galaxy, every star, every planet, every structure built over 13.8 billion years of cosmic evolution, will be erased and overwritten with new physics. The Higgs field is the foundation of reality. It defines what mass means. It determines which particles exist and how they interact. Change the field, and you change everything. We exist because the field has the value it has. If the value changes, we stop existing. Not in the sense of dying, but in the sense of never having been possible in the first place. The universe inside the bubble is not our universe. It is something else, something where the rules are different, and those rules do not allow for atoms, molecules, or life as we know it. Imagine a pencil balanced on its tip. It stands upright, perfectly still. Technically, this is a stable configuration. The pencil is not moving. No forces are acting to push it over. But you know intuitively that this stability is temporary. The slightest vibration, the tiniest air current, even a quantum fluctuation in the positions of the pencil's atoms will eventually tip it. When it tips, it falls. And once it starts falling, it does not stop until it reaches the table. The table is the true stable state. The balanced pencil is a false stable state. The Higgs field is the pencil. Our vacuum is the balanced configuration. The true vacuum is the table. Physicists use the term metastable to describe this situation. Metastable means stable for now, but not forever. The false vacuum is a local energy minimum. Small perturbations will not dislodge the field. It sits comfortably in its valley, and ordinary processes cannot give it enough energy to escape. But quantum mechanics introduces a loophole. The field does not need to be given energy. It can borrow energy temporarily through quantum uncertainty and tunnel through the barrier to the other side. This is not speculation. Quantum tunneling is a well-established phenomenon. Particles tunnel through barriers constantly. Radioactive decay happens because particles tunnel out of atomic nuclei. The sun shines because protons tunnel through the electromagnetic repulsion barrier, fuse into helium. Tunneling is real, observed, and fundamental to how the universe operates. The question is not whether the Higgs field can tunnel, the question is when. The probability of tunneling depends on the shape of the energy barrier. A high, wide barrier makes tunneling rare. A low, narrow barrier makes it common. For the Higgs field, calculations based on the measured particle masses show the barrier is extraordinarily high and wide. The probability of tunneling at any given point in space in any given second is unimaginably small. Physicists estimate the rate at roughly 10 to the power of minus 100 per cubic meter per second. That is a decimal point followed by 99 zeros before you reach a 1. This number is so small it defies comprehension. If you watched a single cubic meter of space for the entire current age of the universe, 13.8 billion years, the probability of observing a vacuum decay event in that volume is effectively zero. But the universe is not a single cubic meter. The observable universe contains roughly 10 to the power of 80 cubic meters. And time does not stop at 13.8 billion years. The universe will continue existing for trillions of years, potentially forever if current expansion models hold. When you multiply an infinitesimal probability by an enormous volume and an enormous time span, the result is no longer negligible. The cumulative probability of vacuum decay somewhere, at some point in the future, approaches certainty. It is not a question of if, it is a question of when. Some calculations put the expected lifetime of our false vacuum at 10 to the power of 100 years. Others suggest 10 to the power of 500 years or more, depending on uncertainties in the top quark mass and other parameters. These numbers are so large they lose meaning, is incomprehensibly longer than the current age of the universe. It is longer than the time it will take for every star to burn out, for every black hole to evaporate, for protons themselves to decay if they are unstable. By any human or even cosmic standard, the vacuum is stable. but forever is longer than... If the universe lasts forever, and the probability of decay is non-zero, then decay is inevitable. This is a hard truth that physics cannot escape. The false vacuum is not a permanent state. It is a temporary one. We are living on borrowed time. Now consider another possibility. Vacuum decay might not wait trillions upon trillions of years. It might already be happening. The universe is vast beyond comprehension. The observable universe extends 46 billion light-years in every direction. But that is just the part we can see. The full universe is likely much larger, possibly infinite. If vacuum decay nucleates in a distant region billions of light-years away, we would not know. The bubble expands at light speed, but light from that region has not reached us yet. Imagine a bubble nucleating 10 billion light-years away, 10 billion years ago. The bubble has been expanding at light speed ever since. It is now a sphere 20 billion light-years in diameter, consuming galaxies by the trillions, but we see none of this. The light carrying information about the decay has not reached us. We look out into the universe and see galaxies, stars, and structure, all apparently stable and obeying the laws of physics we know. We have no idea that a wall of annihilation is racing toward us, closing the distance by 300,000 kilometers every second. There is no way to detect it. No signal can outrun the bubble because the bubble moves at light speed. Gravitational waves travel at light speed. Electromagnetic radiation travels at light speed. Neutrinos, for practical purposes, travel at light speed. Every possible warning signal arrives at the same moment the bubble does. You would not see the stars ahead of you wink out. You would not detect a disturbance in the cosmic microwave background. You would not feel a tremor in space-time. The bubble would simply arrive, and in that instant everything you are and everything you know would cease to exist. This is the existential horror of the false vacuum. It is not just that the universe could end. It is that the universe could already be ending, and we are powerless to know. We exist in a bubble of ignorance, surrounded by a horizon beyond which information cannot reach us. Somewhere beyond that horizon, the true vacuum might already dominate. The wave of destruction might already be underway, propagating through space, erasing structure, rewriting physics, converting the universe sector by sector into something unrecognizable. And even if it has not started yet, it will. The math is clear. The false vacuum is not the ground state. Nature prefers lower energy. The transition is allowed by quantum mechanics. The probability is non-zero. Therefore it will happen. Not might happen, will happen. The only uncertainty is the timescale, and on cosmic timescales, even is finite. We are the pencil balanced on its tip, still upright, still stable. But the table is waiting below. The bubble begins smaller than an atom. Quantum fluctuations allow a microscopic region of space to spontaneously tunnel through the energy barrier. In that infinitesimal volume, the Higgs field shifts to its true vacuum value. The transition releases energy because the true vacuum has lower potential energy than the false vacuum. That energy difference becomes kinetic energy, driving the bubble's expansion. The bubble wall is not made of matter. It is a boundary in field space, a transition zone where the Higgs field rapidly changes from the false vacuum value to the true vacuum value. The thickness of this wall is incredibly small, on the order of the inverse of the energy difference between the two vacua. For the Higgs field, this means the wall is thinner than a proton. The transition happens over distances measured in femtometers, quadrillionths of a meter. Inside the bubble, physics is alien. The Higgs field has a different value, which means particles have different masses. Electrons might be 10 times heavier or 10 times lighter. Quarks could have masses that make protons unstable. The strong nuclear force, which holds atomic nuclei together, depends on quark masses. Change the masses, and nuclei fall apart. Atoms cannot exist. The periodic table is erased. Even if atoms could somehow form, their properties would be unrecognizable. Chemistry depends on the electromagnetic interactions between electrons and nuclei. Those interactions depend on electron mass and charge. Change the electron mass, and the energy levels of atomic orbitals shift. Molecules that are stable in our vacuum become unstable in the true vacuum. DNA, proteins, water, all the molecular machinery of life disintegrates instantly. Stars fare no better. Stellar fusion requires precise conditions. Protons must overcome electromagnetic repulsion to get close enough for the strong nuclear force to bind them. This balance depends on particle masses and coupling constants. In the true vacuum, the balance shifts. Fusion might become impossible, or it might proceed so rapidly that stars explode. Either way, the stars we observe burning steadily for billions of years cannot exist in the true vacuum. Galaxies, clusters, the entire cosmic web of all of it depends on the current laws of physics. Gravity shapes large-scale structure. Electromagnetism governs star formation. The strong and weak nuclear forces control energy generation. Change the underlying parameters, and the structure collapses. The universe inside the bubble is not just different. It is simpler, emptier, devoid of the complexity that allows for stars, planets, and observers. Because the energy released by the vacuum transition is enormous. When the Higgs field drops from the false vacuum to the true vacuum, it releases energy density on the order of the field value squared. For the Higgs field, this is roughly 10 to the power of 34 joules per cubic meter. To put that in perspective, the energy density of matter in the universe today is about 10 to the power of minus 10 joules per cubic meter. The vacuum energy difference is 44 orders of magnitude larger. This energy drives the bubble's expansion. The wall accelerates outward, approaching light speed almost instantly. Once the wall reaches light speed, it stays there. There is no friction in empty space to slow it down. The bubble expands as a perfect sphere, growing by 300,000 kilometers every second. In 1 year, the bubble expands by about 10 trillion kilometers, roughly 1 light year. In a billion years, it expands by 1 billion light years, consuming everything in its path. Nothing inside the bubble survives the transition. The passage of the wall is not gradual. It is instantaneous from the perspective of any observer. The next moment, the wall passes through you. The Higgs field at your location transitions to the true vacuum value. Every particle in your body suddenly has a different mass. The atoms holding you together are no longer stable. The chemical bonds break. The nuclei disintegrate. You do not have time to perceive what is happening because perception requires neurons, which require stable atoms, which require the false vacuum. You are erased in a time frame shorter than the time it takes light to cross a proton. The wall does not just destroy matter, it destroys information. Every configuration of particles, every pattern, every structure that existed in the false vacuum is overwritten. The bubble interior is not empty space, it is true vacuum, a state with different physical laws, but those laws do not permit the complexity of the false vacuum. Stars, planets, life, consciousness, all of these are emergent phenomena made possible by the specific values of the fundamental constants in our vacuum. Change the constants, and the phenomena disappear. This is not death in any conventional sense. Death implies a transition from a living state to a non-living state, but the underlying physical substrate persists. A dead organism is still made of atoms. Those atoms still obey the laws of chemistry. They decay, recombine, and return to the environment. Vacuum decay is different. It is ontological erasure. The substrate itself is rewritten. There is no corpse, no remnant, no trace that anything existed before the wall arrived. The universe inside the bubble has no memory of the universe outside. Worse, the bubble cannot be stopped. There is no force in physics that opposes vacuum decay. You cannot build a shield against it because any shield you build is made of matter, and matter depends on the false vacuum. When the wall arrives, the shield transitions along with everything else. You cannot escape by moving because the wall moves at light speed. Accelerating to near light speed only delays the inevitable by a relativistic time dilation factor, buying you seconds or minutes at most. You cannot collapse the bubble by injecting energy. Adding energy to the true vacuum does not make it transition back to the false vacuum. The true vacuum is the ground state. It is stable. Energy added to it simply becomes radiation, or particles consistent with the true vacuum's physics, not a restoration of the false vacuum. The transition is one way, irreversible, final. The bubble, once nucleated, will expand until it has consumed the entire universe. If the universe is infinite, the bubble will expand forever, always encountering new regions of false vacuum to convert. If the universe is finite, the bubble will eventually convert the entire volume, leaving nothing but true vacuum. Either way, the outcome is the same. The universe we inhabit, the universe capable of supporting complexity, structure, and life, will cease to exist. It will be replaced by something simpler, colder, and utterly inhospitable to everything we recognize as real. 300,000 kilometers per second. This is the speed of light, the cosmic speed limit, and the speed at which the bubble wall expands. Nothing in the universe moves faster. Causality itself is limited by this speed. Information cannot propagate faster than light. Forces cannot act faster than light, and warnings cannot travel faster than light. This creates an inescapable trap. If a vacuum decay bubble nucleates somewhere in the universe, no signal announcing its existence can reach you before the bubble itself does. Light emitted from the bubble wall travels at light speed. The wall travels at light speed. They move in lockstep. The first photon carrying information about the bubble's existence arrives at your location at the exact same instant the wall does. There is no advance notice. No early warning system is possible even in principle. Imagine standing on a beach watching the horizon. A tsunami is approaching, but this tsunami is different. It moves at the speed of light, and it does not travel through water. It travels through space-time itself. You see the ocean. You see the sky. Everything appears normal. Then, without any perceptible transition, the wave is upon you. There is no moment where you see it coming, no moment where you brace for impact. The wave and the awareness of the wave arrive simultaneously, and in that same instant you cease to exist. From your reference frame, the experience would be nothing. You cannot experience your own annihilation because experience requires time, and the wall does not give you time. The neural signals in your brain that constitute consciousness propagate at speeds far slower than light. Electrochemical signals in neurons travel at roughly 100 meters per second. The bubble wall moves at 300,000 kilometers per second, 3 million times faster. Your neurons do not have time to register the event. There is no pain, no fear, no final thought. One moment you exist, the next moment the physics underlying your existence has changed, and you do not. But the wall does not simply erase you. It erases your past. Not literally in the sense of time travel, but in the sense that all evidence of your existence vanishes. Your body disintegrates into a plasma of particles with wrong masses. Those particles decay or recombine into configurations that obey the true vacuum's physics. The atoms that made up your body no longer exist. The molecules that stored your memories no longer exist. The structure of your brain, the physical substrate of your thoughts, is overwritten at the most fundamental level. Every human artifact suffers the same fate. Buildings, cities, spacecraft, data archives, all of it is made of atoms. When the wall passes, the atoms transition. Steel loses its strength because the electron masses change and metallic bonds break. Concrete crumbles because silicon and calcium compounds are no longer stable. Digital data stored in magnetic or electronic form is erased as the materials undergo phase transitions. Nothing survives. Civilization is not destroyed. It is deleted. Earth itself does not survive. The planet is held together by gravity and electromagnetic forces. Gravity depends on mass, and mass depends on the Higgs field. Change the Higgs field, and the gravitational binding energy of the planet changes. The electromagnetic forces holding atoms in the crust and mantle together also change. The planet does not have time to adjust gradually. The wall passes through at light speed. In less than 1/20th of a second, the entire planet transitions. The result is catastrophic. The sudden change in binding energies releases energy comparable to the planet's gravitational potential energy. Earth does not simply fall apart. It explodes. The sun experiences a worse fate. Stars are delicate balances between gravity pulling inward and pressure pushing outward. That pressure comes from fusion in the core, and fusion depends on the masses of protons and the strength of the nuclear forces. In the true vacuum, those parameters are different. Fusion might stop entirely, or it might run away uncontrollably. Either way, the balance is destroyed. The sun either collapses into a dense remnant or explodes in a burst of radiation. Neither outcome matters because the sun's constituent particles are already transitioning to the true vacuum state. The star is not just dying, it is being rewritten. The galaxy fares no better. The Milky Way contains 200 billion stars, each undergoing the same transition. The supermassive black hole at the galactic center, 4 million times the sun's mass, transitions along with everything else. Black holes are not immune. They are regions of space-time where gravity is extreme, but they still obey the laws of physics. Change the laws and the black hole changes. Its event horizon, the boundary beyond which nothing can escape, depends on the gravitational constant and the speed of light. If those constants shift, the horizon shifts. The black hole might evaporate instantly, or it might grow explosively. Astrophysicists do not know because the physics inside the true vacuum is unknown, but it does not matter. The black hole is inside the bubble, subject to the true vacuum's rules, and those rules do not support the structures we observe. The cosmic web, the largest structure in the universe, dissolves. Galaxy clusters, filaments, voids, all of it is held together by gravity acting over billions of years. The wall crosses the observable universe in roughly 46 billion years. That sounds like a long time, but it is finite. Every galaxy, every cluster, every structure built since the Big Bang 13.8 billion years ago is consumed and overwritten. The universe inside the bubble becomes a featureless expanse governed by physics that does not allow complexity. And you cannot see it coming. This is the critical point. If the bubble nucleated, we would not know. The bubble is now 20 billion light-years in diameter, encompassing countless galaxies. But light from those galaxies, showing their destruction, has not reached us. We look at the sky and see galaxies shining steadily, apparently stable, obeying the physics we understand. We have no idea they no longer exist. We are seeing their past, the light they emitted before the wall arrived. The wall is still coming, closing the distance at 300,000 kilometers per second, and we cannot detect it. Even if we could somehow detect the bubble, there is nothing we could do. You cannot outrun light. Accelerating to 99% of light speed only buys a factor of 7 in time dilation. If the bubble is 1 year away, gives you 7 years subjective time before it catches you, then what? You cannot accelerate forever. You run out of energy, you run out of space to flee into, and even if you could accelerate arbitrarily close to light speed, you are only delaying, not escaping. The bubble is infinite in extent once it starts. There is no edge to fly beyond. Some physicists have speculated about escaping into a black hole. The idea is that inside a black hole, space-time is so warped that the inward direction becomes time-like. You fall toward the singularity and nothing, not even light, can escape. Could the bubble wall be stopped by an event horizon? The answer is almost certainly no. The bubble wall is not made of particles. It is a transition in the vacuum state itself. Space-time inside the bubble still exists. It is just governed by different field values. The black hole's event horizon is a feature of space-time geometry, and that geometry depends on the stress-energy content, which depends on the vacuum state. When the wall passes through the black hole, the vacuum inside transitions. The black hole's properties change. You're not safe inside. You're just trapped in a region where the laws of physics are rewriting themselves even more violently than outside. There is no shelter, no defense, no escape. The bubble wall is the ultimate predator, moving at the maximum possible speed, destroying everything in its path and giving no warning. It is not hostile. It is not targeting you. It is simply a consequence of physics, a system transitioning to a lower energy state. You are collateral damage in a process that operates on scales vastly larger than human concerns. The universe does not care whether you exist. It will transition to the true vacuum because that is what the equations allow. And when it does, you will not even have time to realize it is happening. In 2012, physicists knew they had a problem the moment the Higgs mass was confirmed. The number itself was not surprising. Predictions had narrowed the range to between 115 and 135 giga-electron volts, based on indirect measurements from earlier experiments. But confirming the exact value allowed precise calculations of vacuum stability, and those calculations revealed something unsettling. The stability of the Higgs vacuum depends on two particles, the Higgs boson itself and the top quark. The top quark is the heaviest fundamental particle known, with a mass of about 173 giga-electron volts. It interacts with the Higgs field more strongly than any other particle. This interaction affects the shape of the Higgs potential energy curve through quantum corrections. At high energy scales, the top quark's contribution drives the Higgs potential downward, creating the second, deeper minimum at enormous field values. Physicists input the measured Higgs mass and top quark mass into the standard model equations and calculated how the Higgs potential behaves at high energies. The result was unambiguous. The potential develops a second minimum at field values around 10 to the power of 18 giga-electron volts, roughly a billion times larger than the current vacuum value. At that second minimum, the energy is lower than at our current minimum. We are not in the ground state. we are in a metastable state. The barrier separating the two minima is high. Climbing from our current vacuum value to the peak of the barrier requires reaching 12 giga-electron-volts. This is an energy scale far beyond anything accessible to particle colliders. The Large Hadron Collider reaches energies of about 10,000 giga-electron-volts, 8 orders of magnitude below the barrier height. Classical physics says the field cannot climb the barrier, it does not have enough energy. But quantum tunneling does not require climbing. It allows the field to appear on the other side of the barrier without traversing the space in between. The probability of tunneling depends exponentially on the action, a quantity that encodes the barrier's height and width. For the Higgs potential, the action is enormous, leading to tunneling probabilities of roughly 10 to the power of minus 500 per cubic meter per second in some estimates. Other calculations, higher order quantum corrections, give rates as high as. These numbers span a huge range, but they share one feature. They are all incomprehensibly small. To translate them into something meaningful, physicists calculate the expected lifetime of the vacuum. This is the time it would take for a vacuum decay event to occur somewhere in a volume comparable to the observable universe. The calculation involves multiplying the tunneling rate by the volume of space and the duration of time. The result depends sensitively on the exact values of the Higgs and top quark masses. If the Higgs mass were 5 giga-electron-volts heavier, the vacuum would be absolutely stable. The second minimum would disappear, or it would be higher in energy than our current minimum. We would be safe. Lighter, the barrier would be lower, and the vacuum would decay rapidly, likely during the Big Bang. The universe would never have developed structure. Instead, we are balanced on a knife edge. The measured places us squarely in the metastable region, will not last forever. The most optimistic estimates put the vacuum's lifetime at 10 to the power of 600 years. The most pessimistic, accounting for uncertainties and possible new physics, put it as low as is a number so large it defies intuition. For comparison, the current age of the universe is about 10 to the power of 10 years. 10 to the power of 100 is 90 orders of magnitude larger. By the time of past, every star will have burned out. Every black hole will have evaporated through Hawking radiation, a process that takes for the largest black holes. Protons, if they are unstable as some theories suggest, will have decayed. The universe will be a cold, dark expanse containing only photons, neutrinos, and whatever exotic particles remain. And even then, the vacuum decay might not have occurred, but not infinity. It is a finite number. If the universe continues existing indefinitely, and if the probability of vacuum decay is non-zero, then decay becomes a SIP but when. And the when could be tomorrow. Probability does not care about fairness or timing. An event with a probability of second could happen in the next second, or it could wait 10 to the power of 100 seconds. The expected time is, but that is an average over many trials. In a single trial, which is what we have, anything can happen. Physicists are unsettled by this for several reasons. First, the metastability is not predicted by any deeper theory. It is an accident of the measured particle masses. If the Higgs mass was slightly different, the conclusion would be completely different. This suggests we do not understand why the masses have the values they do. The standard model does not predict particle masses. They are input parameters, measured experimentally. The fact that these parameters place us in a metastable vacuum feels arbitrary and unexplained. Second, the metastability implies our universe is temporary. Everything we observe, every law of physics we have discovered, is valid only within the false vacuum. Outside the bubble, or after the bubble passes, none of it applies. The standard model, general relativity, quantum mechanics, all of these are descriptions of false vacuum physics. They are not fundamental truths. They are emergent properties of a temporary configuration. This undermines the sense that we are uncovering eternal laws of nature. Third, the fine-tuning bothers people. The Higgs mass is 125 giga-electron-volts. If it were 120 or 130, the vacuum stability would be dramatically different. The fact that we landed in the narrow metastable range, where the universe lasts long enough for life to develop but not forever, seems suspicious. Some physicists invoke the anthropic principle. We observe a metastable vacuum because only in such a vacuum can observers exist long enough to make observations. In a completely stable vacuum, nothing interesting might happen. In a completely unstable vacuum, structure never forms. We are here because the vacuum is just barely stable enough. This explanation is philosophically unsatisfying to many. It replaces a dynamical explanation with a selection effect. It says we should not be surprised to find ourselves in an unlikely situation because only in that situation could we exist to be surprised. But it does not explain why the situation exists in the first place. It only explains why we observe it. Fourth, the metastability raises the possibility that new physics exists at energy scales we have not yet probed. The standard model might be incomplete. Supersymmetry, extra dimensions, or other extensions could modify the Higgs potential at high energies, changing the vacuum stability calculation. Some of these extensions stabilize the vacuum, others make it more unstable. Without experimental evidence for new physics, we cannot know which, if any, applies to our universe. The measurements continue. Physicists at CERN and other laboratories are refining the Higgs and top quark mass measurements, reducing uncertainties. Every additional decimal place of precision shifts the vacuum stability calculation slightly. As of the latest measurements, the central values still place us in the metastable region, but the uncertainties are large enough that absolute stability is not ruled out. If future measurements shift the Higgs mass upward by just a few giga-electron volts, we might discover we are safe after all. But the current best estimate is that we are not safe. We are living in a universe that is fundamentally unstable, held together by a quantum barrier that will eventually be breached. The math is clear. The standard model, our most successful theory of particle physics, predicts our own annihilation. Not through some external threat, but through an internal instability written into the fabric of reality itself. The vacuum does not decay spontaneously in most of space. The probability is too low. But certain events concentrate energy in small regions, creating conditions where tunneling becomes more likely. These events are rare, but the universe is large and old. Somewhere, at some time, one of these triggers might nucleate the bubble. Particle collisions at extreme energies are the most obvious candidates. When two protons collide at nearly light speed, their kinetic energy converts into mass energy, creating a shower of particles. The Large Hadron Collider produces collisions with energies around 10,000 giga-electron volts. This is far below the energy scale where the Higgs potential becomes unstable, but it is not zero. Each collision creates a localized region of high energy density. If the energy happens to fluctuate into the right configuration, it could seed a vacuum decay bubble. Physicists calculated this risk before turning on the Large Hadron Collider. The conclusion was reassuring. The energy density achieved in collider experiments is lower than the energy density naturally produced by cosmic rays. Cosmic rays are high-energy particles, mostly protons, that bombard Earth from space. The most energetic cosmic rays have energies exceeding 10 to the power of 11 giga-electron volts, 10 million times higher than anything the Large Hadron Collider produces. These cosmic rays collide with particles in Earth's atmosphere constantly, and they have been doing so for billions of years. If such collisions could trigger vacuum decay, it would have happened already. The fact that we still exist means collider experiments are safe. But cosmic rays themselves raise a troubling question. The highest energy cosmic rays carry energies that should not exist according to standard astrophysics. Particles with energies above should interact with the cosmic microwave background radiation, losing energy through pion production. This process, called the GZK cutoff, limits the distance such particles can travel to about 100 million light-years. Yet we detect cosmic rays with energies above this cutoff. Either they are produced nearby, within 100 million light-years, or something about our understanding of particle physics is wrong. If ultra-high-energy cosmic rays come from nearby sources, those sources are accelerating particles to energies that dwarf anything achievable in laboratories. Supermassive black holes, colliding neutron stars, or exotic processes near event horizons might produce such particles. Each collision between an ultra-high-energy cosmic ray and an atmospheric nucleus is a miniature experiment probing energy scales beyond human technology. These experiments have been running for billions of years across the entire universe. The fact that vacuum decay has not occurred suggests the energy threshold is much higher than the highest cosmic ray energies. But there is a loophole. Cosmic rays interact with individual particles. The energy is spread over the collision products, diluting the energy density. Vacuum decay requires concentrating energy in a small region of space and sustaining it long enough for quantum tunneling to occur. This might require conditions more extreme than cosmic ray collisions provide. it might require astrophysical events that concentrate energy more efficiently. Black hole collisions are one possibility. When two black holes merge, they release energy in the form of gravitational waves. The merger of two black holes with masses of 30 times the Sun releases energy equivalent to 3 solar masses, converted entirely into gravitational wave energy in a fraction of a second. This energy is spread over a large volume, but near the merging black holes the energy density is extreme. Space-time itself warps violently. Quantum fluctuations in the Higgs field, normally negligible, might be amplified by the intense curvature. The Laser Interferometer Gravitational Wave Observatory, LIGO, has detected dozens of black hole mergers since 2015. Each merger is a probe of physics in extreme conditions. None have triggered vacuum decay, which suggests the energy density, even near merging black holes, is insufficient. But LIGO detects only nearby mergers within a few billion light-years. The universe is far larger. Black hole mergers occur constantly throughout the cosmos. Each one is a potential nucleation site. Evaporating black holes present another risk. Stephen Hawking predicted in 1974 that black holes emit radiation due to quantum effects near the event horizon. This Hawking radiation causes black holes to lose mass over time. Small black holes evaporate faster than large ones. A black hole with the mass of a mountain would evaporate in a time comparable to the current age of the universe. As the black hole shrinks, its temperature increases. In the final moments before complete evaporation, the black hole becomes incredibly hot, releasing a burst of high-energy particles and radiation. Primordial black holes, formed in the early universe from density fluctuations, could be evaporating now. If primordial black holes with masses around 10 to the power of 11 kilograms exist, they would be reaching the end of their lives today, 13.8 billion years after the Big Bang. The final evaporation would release energy equivalent to millions of megatons of TNT in a fraction of a second. The energy density near the evaporating black hole could reach values comparable to the early universe, potentially destabilizing the Higgs field. No one has detected a primordial black hole evaporation event. This suggests either they do not exist in large numbers, or their evaporation does not trigger vacuum decay. But absence of evidence is not evidence of absence. The universe is vast. If primordial black holes are evaporating in distant regions, we would not know until the light from the event reached us, and by then, if it triggered vacuum decay, the bubble would arrive simultaneously. Cosmic inflation offers another mechanism. Inflation is the theory that the universe underwent a period of exponential expansion in its first fraction of a second. During inflation, the universe was in a high-energy vacuum state. When inflation ended, the universe transitioned to the current low-energy vacuum, but this transition might not have been uniform. Different regions of space might have transitioned at different times, creating a patchwork of vacuum states. If the universe is far larger than the observable region, and if inflation created multiple vacuum domains, we might be living in one domain while other domains exist beyond our horizon. Some of those domains might already be in the true vacuum. The boundaries between domains would be expanding, converting false vacuum to true vacuum. If such a boundary exists beyond our cosmic horizon and is moving toward us, we would not know until it arrived. Eternal inflation takes this idea further. In eternal inflation, the inflationary process never completely ends. It continues in some regions of space while ending in others. This creates a multiverse where different regions have different vacuum states, different physical constants, and different laws of physics. Our observable universe is one bubble in an infinite froth of bubbles. Some bubbles are stable, some are metastable, some have already decayed. We exist in a metastable bubble because stable bubbles might not support complexity, and decayed bubbles do not support anything. This framework makes vacuum decay almost inevitable. Somewhere in the infinite multiverse, a metastable bubble is decaying right now. The bubble of true vacuum expands, colliding with neighboring false vacuum bubbles. Each collision converts more space to true vacuum. Over infinite time, the true vacuum dominates. Our bubble has not decayed yet, but it will. The only question is whether the decay nucleates spontaneously within our bubble, or whether it arrives from outside as an expanding domain wall. Even if no external trigger exists, the vacuum can decay spontaneously. This is the pure quantum tunneling scenario. Quantum mechanics allows the Higgs field to fluctuate. Normally, these fluctuations are small and short-lived, but occasionally, a fluctuation might be large enough to push the field over the barrier. The probability is infinitesimal for any given point in space at any given time, but integrated over the entire universe and over cosmic timescales, the cumulative probability is non-negligible. Calculating the rate requires understanding quantum field theory in curved spacetime. The expanding universe affects vacuum decay rates because expansion dilutes energy density and stretches wavelengths. Some calculations suggest expansion suppresses vacuum decay, extending the vacuum's lifetime. Others suggest expansion enhances decay in certain conditions. The uncertainties are large because the calculations involve approximations and assumptions about physics at energy scales we cannot directly test. One unsettling conclusion is robust across all calculations. If the vacuum is metastable, it will eventually decay. No trigger is required. Quantum mechanics guarantees that improbable events occur given enough time. The vacuum state is not a fixed, eternal feature of the universe. It is a temporary configuration, maintained only by the height of the energy barrier and the low probability of tunneling. Over infinite time, the barrier will be breached. The universe will transition, and everything that exists in the false vacuum will be erased. We are living in the gap between nucleation events, a window of time where the vacuum has not yet decayed. This window has lasted 13.8 billion years. It might last another, or it might end in the next second. We cannot know. We cannot predict when or where the first bubble will nucleate. We can only calculate probabilities, and probabilities do not tell you what will happen. They tell you what might happen. The dice are rolling constantly, every second, in every cubic meter of space. So far they have not come up decay, but eventually they will. The Standard Model of particle physics is the most successful scientific theory ever constructed. It describes three of the four fundamental forces: electromagnetism, the weak nuclear force, and the strong nuclear force. It accounts for all known elementary particles and predicts their interactions with extraordinary precision. Experiments have tested the Standard Model's predictions to accuracies of 1 part in 10 billion in some cases. No confirmed observation contradicts it. This success makes the vacuum metastability problem deeply disturbing. The same equations that predict particle masses, decay rates, and scattering cross-sections with perfect accuracy also predict that the universe is unstable. The theory does not fail in exotic conditions or at untested energy scales. It fails at predicting the long-term fate of the vacuum we inhabit. The math says we should not be here, or more precisely, we should not be here for much longer on cosmic timescales. Physicists expected the Standard Model to be incomplete. It does not include gravity, which is described by general relativity, a separate framework. It does not explain dark matter, the invisible substance that makes up 85% of the matter in the universe. It does not explain why the universe contains more matter than antimatter. It does not predict the masses of particles or the strengths of forces. These values are free parameters, measured experimentally and plugged into the equations. A truly fundamental theory should predict these values from deeper principles. But the Standard Model was supposed to be correct within its domain of applicability. It should accurately describe particles and forces at energies below a few thousand giga-electron-volts, the scale where new physics might emerge. The vacuum metastability suggests this assumption is wrong. Either the Standard Model is missing something crucial, or the universe is genuinely unstable and we are living on borrowed time. The metastability crisis has several layers. First, it implies the universe is not in its ground state. This violates the expectation that nature prefers minimum energy configurations. Systems evolve toward lower energy. Water flows downhill. Heat dissipates. Unstable nuclei decay. The universe itself should relax to its lowest energy state. Yet here we are, still in a false vacuum. Why has the transition not occurred? One answer is that the barrier is high and tunneling is rare. This is true, but it is not satisfying. The barrier height depends on the Higgs and top quark masses, which are free parameters in the Standard Model. Why do these masses have values that create a high barrier? Why are we not in a universe where the barrier is low and vacuum decay happened immediately after the Big Bang? The Standard Model offers no answer. Second, the metastability implies fine-tuning. The measured Higgs sits in a narrow range between absolute stability and rapid decay. If the mass were a few percent higher, we would be safe. If it were a few percent lower, the universe would have decayed long ago. The range of masses that produce a metastable vacuum lasting billions of years is small compared to the range of possible masses. Why did nature choose a value in this narrow window? Fine-tuning is not illegal in physics, but it is suspicious. When a theory requires parameters to have very specific values to match observations, it suggests the theory is incomplete. Either there is a deeper principle explaining why the parameters have those values, or we are observing a selection effect. The anthropic principle offers a selection effect explanation. Universes with stable vacua might be sterile, lacking the complexity needed for life. Universes with unstable vacua destroy themselves before life emerges. We are in a metastable universe because that is the only type of universe where we could be. This explanation works logically but feels unsatisfying. It replaces a dynamical explanation with an observational selection bias. It says the universe is the way it is because if it were different, we would not be here to ask why. This is true but not explanatory. It does not tell us why metastable universes exist at all, only why we happen to find ourselves in one. Third, the metastability connects to the hierarchy problem, one of the deepest puzzles in particle physics. The Higgs mass is about 125 giga-electron-volts. Quantum corrections to this mass come from virtual particles that briefly pop into existence and affect the Higgs field. The top quark, being heavy and strongly coupled to the Higgs, contributes large corrections. Naively, these corrections should drive the Higgs mass up to the Planck scale, around 10 to the power of 19 giga-electron-volts, the energy scale where gravity becomes as strong as the other forces. Yet the Higgs mass is 17 orders of magnitude smaller than the Planck scale. This means the quantum corrections must cancel almost perfectly, leaving a tiny residual value. This cancellation requires fine-tuning the parameters of the standard model to 1 part in 10 to the power of 17. Such fine-tuning is technically possible but seems unnatural. Physicists suspect a deeper mechanism enforces the cancellation, but no confirmed theory provides it. Supersymmetry was the leading candidate for solving the hierarchy problem. Supersymmetry predicts that every particle has a heavier partner with opposite spin statistics. The contributions of particles and their superpartners to the Higgs mass cancel naturally, stabilizing the mass at low values without fine-tuning. Supersymmetry also predicts that the Higgs potential is modified at high energies, potentially stabilizing the vacuum. But the Large Hadron Collider has found no evidence for supersymmetry. The predicted superpartner particles have not appeared, even at energies where they were expected. Either supersymmetry is broken at higher energies than anticipated, or it does not describe our universe. Without supersymmetry or a similar mechanism, the hierarchy problem remains unsolved, and the vacuum metastability remains unexplained. Fourth, the metastability suggests the universe has a finite lifetime. This contradicts the expectation that fundamental laws are eternal. If the vacuum can decay, and if it will decay eventually, then the current laws of physics are temporary. The standard model and general relativity are not descriptions of eternal truths. They are descriptions of how fields behave in the false vacuum. In the true vacuum, different laws apply. This makes physics a historical science rather than a search for timeless principles. Some physicists find this philosophically troubling. Science traditionally seeks laws that are universal and unchanging. Newton's laws, Maxwell's equations, Einstein's field equations are supposed to describe reality at all times and places. The vacuum metastability implies this assumption is wrong. The laws we discover are contingent on the vacuum state we inhabit. Change the vacuum, and the laws change. Reality is not governed by eternal principles but by temporary configurations. Others argue this is no different from other phase transitions. Water can exist as ice, liquid, or vapor. The properties of water differ in each phase, but the underlying molecular structure is the same. Similarly, the universe can exist in different vacuum states. The underlying quantum fields are the same, but their configurations differ, leading to different emergent laws. The true vacuum is not a different universe. It is the same universe in a different phase. But this analogy breaks down because the transition is irreversible and catastrophic. Ice melting into water does not destroy the molecules. Vacuum decay destroys the structures built in the false vacuum. Atoms, stars, galaxies, all of it is erased. The transition is not a gentle phase change. It is an ontological overhaul. Fifth, the metastability raises questions about the early universe. If the vacuum is metastable now, was it metastable during the Big Bang? The early universe was far hotter and denser than today. Energies reached scales where the Higgs potential might have been very different. Some calculations suggest the universe passed through the unstable region during inflation or shortly after. If so, Why did vacuum decay not occur then? One possibility is that the universe was in the true vacuum during the Big Bang and transitioned to the false vacuum as it cooled. This requires a mechanism for the transition, which is not part of the standard model. Another possibility is that quantum fluctuations during inflation were so violent that the Higgs field explored the entire potential landscape, including regions beyond the barrier. Yet somehow, the field ended up in the false vacuum rather than the true vacuum. Why? These questions have no definitive answers. The metastability crisis is not a failure of the standard model to predict specific phenomena. It is a failure to explain why the universe exists in a state that the model says should be temporary. The theory works perfectly for describing particles and forces, but it cannot explain its own domain of validity. This suggests something fundamental is missing, either in the standard model or in our understanding of vacuum states and quantum field theory. Physicists are unsettled because the metastability is not a problem they can ignore. It is not a minor inconsistency or an unexplained detail. It is a prediction that the universe will end. Not in some vague, distant future, but through a specific calculable mechanism. The standard model hands us the tools to compute our own annihilation, and those tools say the annihilation is not just possible but inevitable. The only uncertainty is when. If the universe can exist in multiple vacuum states, and if each state has different physical laws, then perhaps the universe we observe is not the only one. This idea leads to the multiverse, a framework where countless universes exist with different properties. Some universes inhabit a metastable universe not because it is typical, but because it is the only type where observers like us can exist long enough to ask questions. This is the anthropic principle applied to vacuum states. The principle states that observed properties of the universe must be compatible with the existence of observers. If the vacuum were completely unstable, it would decay within microseconds of the Big Bang. No stars would form, no planets would coalesce, no life would emerge. Observers require a universe that lasts at least billions of years, long enough for stellar nucleosynthesis to produce heavy elements, for planets to form, and for biological evolution to create complexity. A metastable vacuum lasting easily satisfies this requirement. The anthropic explanation does not predict the Higgs mass. It only explains why we observe a mass in the narrow range that produces long-lived metastability. In a multiverse where different regions have different Higgs masses, the vast majority of regions are uninhabitable. Regions with very light Higgs bosons decay instantly. Regions with very heavy Higgs bosons might be stable, but lack other properties necessary for life, such as the right balance of forces to allow chemistry. We find ourselves in a metastable region because that is where observers can exist. This reasoning frustrates many physicists. It replaces predictive power with a selection effect. Instead of calculating what the Higgs mass must be from first principles, the anthropic principle says the mass can be almost anything, and we observe one value simply because we exist. This feels like giving up on explanation. Science traditionally seeks causal mechanisms, not existential coincidences. But the anthropic principle gains support from the multiverse framework, which arises naturally from eternal inflation. Inflation is the theory that the early universe underwent exponential expansion, driven by a scalar field in a high-energy state. As inflation proceeded, quantum fluctuations caused different regions to exit inflation at different times. Each region that exited became a bubble universe, expanding and cooling into the low-energy vacuum we observe today. Stops. While some regions exit and form bubble universes, other regions continue inflating. This creates an infinite fractal structure where new bubbles constantly nucleate within the inflating background. Each bubble is causally disconnected from the others. Light cannot travel between them because the inflating space expands faster than light. Each bubble is, for all practical purposes, a separate universe. Different bubbles can have different vacuum states. During the transition from inflation to the low-energy vacuum, the fields settle into different configurations depending on local quantum fluctuations. The Higgs field might settle into the false vacuum in some bubbles and the true vacuum in others. The cosmological constant, the value of dark energy, might differ between bubbles. Even the fundamental constants like the electron mass or the strength of the strong force might vary if they depend on the vacuum configuration of other fields. This landscape of possibilities is enormous. String theory, a candidate for a unified theory of all forces including gravity, predicts roughly 10 to the power of 500 possible vacuum states, each corresponding to a different configuration of extra dimensions and field values. If string theory is correct, and if eternal inflation populates this landscape, then the multiverse contains 10 to the power of 500 different types of universes, each with different laws of physics. Most of these universes are sterile. In some, the cosmological constant is so large that space expands too rapidly for matter to clump into galaxies. In others, the electron mass is so large that atoms cannot form. In others, the strong force is too weak to bind protons and neutrons into stable nuclei. The parameter space where life is possible is a tiny fraction of the total landscape. But in an infinite multiverse, even a tiny fraction contains infinitely many habitable universes. We live in one of those rare habitable bubbles, not because any law requires it, but because bubbles with that value happen to allow observers. Bubbles with other values exist, but they are empty. No one is there to measure the Higgs mass or to wonder why the universe is the way it is. This explanation is logically consistent but untestable. By definition, other universes in the multiverse are beyond our observation. We cannot see them, visit them, or detect them in any way. The multiverse hypothesis makes no falsifiable predictions. It explains observed properties by appealing to unobservable entities. Some scientists argue this disqualifies it as science. If a theory cannot be tested, it is philosophy, not physics. Others counter that the multiverse is a prediction of inflation, which is testable. Inflation makes specific predictions about the cosmic microwave background radiation, the distribution of galaxies, and the spectrum of gravitational waves. These predictions have been confirmed by observations. If inflation is correct, and if quantum mechanics is correct, then eternal inflation and the multiverse follow as logical consequences. Rejecting the multiverse requires rejecting either inflation or quantum mechanics, both of which are well-tested theories. The debate remains unresolved. But regardless of whether the multiverse exists, the anthropic principle offers a framework for understanding vacuum metastability. If the universe is one of many, and if observers can only exist in universes with certain properties, then the observed properties need not be typical. They need only be compatible with observation. This has a darker implication. If we are in a metastable universe selected by the anthropic principle, then the vacuum must be metastable long enough for observers to exist, but not necessarily longer. The typical lifetime should be just barely sufficient for life to emerge and develop intelligence. Universes that are stable forever are rarer in the landscape than universes that decay after 10 billion or 100 billion years. Therefore, the anthropic principle predicts we should expect to be near the end of the vacuum's lifetime, not at the beginning. This argument, called the doomsday argument in its general form, suggests vacuum decay might be imminent on cosmic timescales. If the vacuum's expected lifetime years, and we are roughly 10 billion years into that lifetime, we are still very early. But if uncertainties in the calculations push the lifetime down to 10 billion years, we are near the end. The vacuum could decay at any moment, and the anthropic principle would not be violated. We existed long enough to become observers. That is all the principle requires. Some physicists reject this reasoning. They argue that the anthropic principle should not predict when events occur, only that they occur in a range compatible with observers. If the vacuum lifetime is 10 billion years, we should expect to find ourselves somewhere in the first few billion years, when star formation is vigorous and planets are forming. Finding ourselves near the very end, just before decay, would be an improbable coincidence. Others argue the opposite. In a multiverse with varying vacuum lifetimes, the number of observers is proportional to the lifetime. Longer-lived universes produce more observers because they have more time for life to emerge on more planets. Therefore, typical observers should find themselves in universes with very long lifetimes, not short ones. The fact that we measure a Higgs mass in the metastable range, rather than the absolutely stable range, is puzzling. It suggests either our calculations are wrong, or we're atypically early in a very long-lived vacuum, or the multiverse hypothesis is incorrect. The anthropic principle also raises questions about the future. If vacuum decay is inevitable, what happens to observers in the far future? Suppose intelligent civilizations arise trillions of years from now, in galaxies formed from material recycled through multiple generations of stars. Those civilizations will measure the same Higgs mass we do. They will calculate the same vacuum lifetime, but they will be closer to the end. If the ECE, a civilization arising at 10 to the power of 90 years, would have only 10 to the power of 10 years remaining. The probability of vacuum decay during their existence would be much higher. Do such civilizations exist? If the multiverse is real, they do, somewhere. And they face the same existential threat we do, but with less time remaining. Some of them might develop technology to detect vacuum decay bubbles at a distance, or to shield themselves somehow. Others might accept their fate and focus on maximizing their existence in the time available. None can escape. The bubble expands at light speed. No technology can outrun it. This paints a bleak picture of the far future. Even if humanity survives every terrestrial threat, climate change, asteroid impacts, supervolcanic eruptions, even if we spread across the galaxy and persist for millions or billions of years, vacuum decay remains an inescapable endpoint. The universe itself is unstable. Reality is temporary. Everything we build, everything we learn, everything we become will be erased when the bubble arrives. The anthropic principle offers no comfort. It explains why we exist in a universe with these properties, but it does not change the properties. We are here because the vacuum is metastable, and because the vacuum is metastable, we will not be here forever. The principle that explains our existence also guarantees our extinction. Quantum mechanics operates on a principle that seems absurd at human scales, but is fundamental at microscopic scales. Particles do not have definite properties until they are measured. They exist in superpositions of multiple states simultaneously. An electron does not orbit an atom in a specific path. It occupies a cloud of probability, existing in all possible positions at once until an observation collapses the wave function. This indeterminacy is not ignorance. It is not that the electron has a definite position we simply do not know. The electron genuinely does not have a definite position. The universe itself has not decided where the electron is until a measurement forces it to choose. This is confirmed by countless experiments. Quantum superposition is real. Heisenberg's uncertainty principle formalizes this indeterminacy. It states that certain pairs of properties cannot be simultaneously known with perfect precision. The more precisely you know a particle's position, the less precisely you can know its momentum. The more precisely you know the energy of a system at a specific moment, the less precisely you can know how long that energy persists. This is not a limitation of measurement technology. It is a fundamental feature of nature. The energy-time uncertainty relation allows systems to briefly violate energy conservation. A system can borrow energy from the vacuum, exist in a higher energy state for a short time, and then return the energy, as long as the borrowed energy multiplied by the time duration is less than Planck's constant. The larger the energy borrowed, the shorter the time it can be borrowed. This allows quantum fluctuations, temporary violations of classical physics, that average out to zero over time. These fluctuations have measurable consequences. The Casimir effect, where two uncharged metal plates placed close together in a vacuum experience an attractive force, arises from quantum fluctuations in the electromagnetic field. Virtual particles, particle-antiparticle pairs that spontaneously appear and annihilate, contribute to the magnetic moment of the electron. The vacuum is not empty, it seethes with fluctuations. The Higgs field participates in these fluctuations. At every point in space, the field value oscillates around its average value of 246 giga-electron-volts. Most fluctuations are small, a few giga-electron-volts above or below the average. These fluctuations are harmless. They do not push the field high enough to approach the barrier separating the false vacuum from the true vacuum. But quantum mechanics allows arbitrarily large fluctuations, as long as they are sufficiently brief. A fluctuation that pushes the field to 10 to the power of 12 giga-electron-volts near the top of the barrier is allowed. It is extraordinarily unlikely, but not impossible. The probability decreases exponentially with the size of the fluctuation, but it never reaches zero. This is the mechanism of vacuum decay. A quantum fluctuation in the Higgs field, occurring in a tiny region of space, pushes the field over the barrier. The field tunnels to the true vacuum. The fluctuation does not have enough energy classically to climb the barrier, but quantum mechanics does not require climbing. The field can tunnel through, appearing on the other side without traversing the intermediate values. Once the field reaches the true vacuum on the other side, it releases energy. The potential energy difference between the false vacuum and the true vacuum converts into kinetic energy, driving the expansion of the bubble. The bubble grows because the system is moving downhill energetically. There is no force to stop it. The probability of this happening at any specific point in space, at any specific moment, is infinitesimal. Calculating the exact probability requires integrating over all possible field configurations, accounting for the shape of the potential barrier and the quantum fluctuations that can surmount it. The result is typically expressed as a decay rate per unit volume per unit time, measured in inverse meters to the fourth power. For the Higgs field, this rate is approximately meter to the fourth power per second, depending. This number is unimaginably small. A cubic meter of space has a volume of 1 meter cubed, which is 1 meter to the third power. To convert the decay rate to probability per cubic meter per second, you multiply by the volume, giving, over the current age of the universe, about 10 to the power of 17 seconds, the probability that a specific cubic meter has decayed 483, essentially zero. But the observable universe contains about, multiply the probability per cubic meter by the number of cubic meters, and you get 10 to the power of minus 403 per second for the entire observable universe. Over the age of the universe, the cumulative probability 386, still essentially zero. Extend the time horizon to Kim and the probability becomes non-negligible. The cumulative probability of at least one decay event somewhere in the observable universe approaches unity. The vacuum will decay, only a question of when. These calculations involve significant uncertainties. The decay rate depends exponentially on the height and width of the potential barrier, which depend on particle masses and coupling constants. Small errors in measuring the Higgs or top quark mass translate into large errors in the decay rate. If the Higgs mass is a few giga-electron volts higher than currently measured, the barrier becomes higher, and the decay rate drops by orders of magnitude. If the mass is lower, the rate increases. Additionally, the calculations assume the standard model is complete up to very high energies. If new physics appears at intermediate scales, it could modify the Higgs potential, changing the barrier shape. Supersymmetry, extra dimensions, or new heavy particles could stabilize the vacuum, making decay impossible, or destabilize it further, making decay more likely. Another uncertainty arises from the expansion of the universe. The calculation of decay rates assumes flat, non-expanding spacetime. But the universe is expanding, driven by dark energy. Expansion affects vacuum decay in complex ways. In some models, expansion suppresses decay by diluting energy density and stretching fluctuations. In others, expansion enhances decay by creating conditions where tunneling is more probable. The interplay between quantum field theory and cosmology is not fully understood. Despite these uncertainties, one conclusion is robust. If the vacuum is metastable, it can decay through quantum tunneling. The probability is not zero. Over sufficiently long times or over sufficiently large volumes, the improbable becomes inevitable. The universe is conducting a quantum experiment at every point in space, every second. Each point is rolling the dice, testing whether a fluctuation large enough to nucleate a bubble occurs. So far, across 13.8 billion years of observable space, the dice have not come up decay, but the dice are loaded against us. The probability of decay increases with time because more opportunities arise. It increases with volume because more space is rolling the dice. The universe is expanding, creating more volume. Therefore, the cumulative probability of decay grows without bound. Eventually, somewhere, a fluctuation will succeed. A bubble will nucleate, and when it does, the cascade is irreversible. Quantum mechanics gives us the mechanism but not the timing. It tells us vacuum decay is possible and inevitable, but it cannot tell us when or where the first bubble will appear. The decay could happen in the next second, in a cubic meter of space in this room. It could happen 1 trillion years from now, in a distant galaxy we will never see. The randomness is fundamental. There is no hidden variable determining the outcome. The universe itself does not know when it will happen. This is the existential weight of quantum uncertainty. We live at the mercy of fluctuations we cannot control, predict, or prevent. The Higgs field is fluctuating constantly everywhere, and each fluctuation is a chance, however small, that reality will rewrite itself. We exist in the gaps between fluctuations, in the moments when the dice come up anything other than decay, and we have no way of knowing how many rolls we have left.